Welcome to Embedded Systems Design at the University of Utah. My name is Pierre-Emmanuel Gaillardon, and I will be your instructor for this semester. I would like us to get started with a couple of administrative points. I would like you guys to keep in mind that embedded systems are a fairly complex topic. And in particular, it's very important to keep an open-mindedness across the entire semester. Some topics may seem familiar to you. You might have expertise in electrical engineering, you might be an expert in computer science. We are kind of mixing everything in this class and be open to seeing this familiar topic in a new light. Embedded system is clearly not computer science. It's not electrical engineering as well. It's something that goes at the junction of both. And you need to develop a complex set of skills that goes beyond your traditional CS or EE knowledge. You need to keep a really open-minded spirit in order to reach that goal. Our class will not be a class-based course. There are ways to teach embedded systems as a pure class-based course, but what I want to do is to hack things. We're learning how to hack material, how to hack embedded systems, and this class will therefore have a very strong lab component. Labs will help you applying concepts, and we will even get started by having a mini project where you will create your own custom embedded system that will stimulate your interest and creativity. Finally, I'd like to point out that several prerequisite knowledge must be acquired. In this class, you will not learn C. It's definitely not about learning C. You'll have to be proficient on your own and being able to acquire the skills you might like at this point. Even though C is our language of choice, we will not learn C per se in this class. You must be aware of that. So as I said, beyond C, there is also quite a bunch of prerequisites. Playing at the interaction between computer science and electrical engineering, you need to, have a general feeling about both of these worlds. Here's a list of common prerequisite knowledge that you should typically have before embarking into embedded systems. You must knowledgeable about programming data structures in C. What are queues, stack, linked lists, trees, dynamic allocation, all that kind of stuff. You need to be familiar about that. You also need to be relatively familiar with microcomputer programming. Have some basic notion about assembly language programming and what a microarchitecture of a modern processor looks like. You're also expected to have knowledge about digital logic. This goes about knowing the basic standard cells, multiplexers, tri-state logic, as well as more sequential topics, finite state machine, and so on and so forth. You will, from time to time, be required to have some basic notion about hardware description languages, VHDL, Verilog. We're not going to use that per se, but if in the product component of this class you decide to include, for example, an FPGA SoC, you might be using these skills. Now, beyond this pure knowledge, you also need to have experience in lab components, and you need to be familiar with test equipments. Multiplexers, oscilloscopes, lab power supply, all that kind of things. And finally, because embedded systems are all about interconnecting the real world into a computer, you need to have some basic notion about discrete analog electrical circuits. That goes about very simple passive devices, resistors, capacitors, inductors. Just sizing an LED, for example, is a very important set of skills, as well as transistors and op-amps and all sorts of active circuits. Obviously, you are expected to have knowledge about that. You're not expected to be proficient in all those topics as long as you're willing to learn any missing knowledge about those different topics. How to get caught up if you don't feel that you are really proficient on those topics. You will have to read the references I've posted already on Canvas. You can also browse the web, or most importantly, please come and bug me or ask your TAs. I would like to point out that it is your responsibility to let us know your difficulties and our duty to help you overcome them. But if we don't know where you struggle, we cannot help you. So please be very proactive, work on time, try to acquire the missing knowledge, and report to me or your TA once again if you're suffering on specific topics. We'll be happy to provide you more examples. We'll be definitely happy to guide you through that difficulty. As I said, I will be your instructor for the entire semester. The class web page is available on Canvas, and feel free to reach out to me either using the Canvas inline messaging system or through my email as provided in these informations. My office is the MEB 2126. I'm available after class or by appointment. Please do not hesitate to reach out to me for any questions and concerns. Teaching assistants will be posted on Canvas. However, I'd like to already point out to our lead teaching assistant, Thomas Becknell, that can be reached out to this email address as well. So, bottom line, any questions, send an email to me or the lead TA. This class will not use textbooks per se. Embedded systems are covering so many various topics that it is very hard to follow a single textbook. However, I would recommend two interesting textbooks for your use. The first one being the Definitive Guide to ARM Cortex-M0 and M0 Plus processors. This book is really the reference written from ARM about all the nitty-gritty details of the Cortex-M0 processors that we will be using in this class. Another textbook is the Introduction to Embedded Systems, a cyber-physical system approach from Edward Lee and Sanjit Cheshia from UC Berkeley. This book is available for free on the following URL and does cover all the topics related to more like system modeling and design methodologies related to embedded systems. We will talk about these design methodologies later down the road in that class. Embedded systems are traditionally taught using the following syllabus, where the instructor will cover the issues of embedded system design using microcontroller systems, programming, and system design. Traditional topics do include microcontroller architectures, embedded software design, interrupt synchronization, as well as all sort of peripheral programming and use, timing generation, serial interface, communication peripherals, analog interfaces, and so on and so forth. However, in the recent years, another way emerged in teaching embedded systems. This approach is called cyber-physical systems focused, and it does consider embedded systems as really a system, not anymore as just a piece of hardware that uses a microcontroller that you need to use. It does consider embedded systems as really a system for which you need to model the specification correctly, and it's only when you have that in place that you can start making the design. In some sense, very similar to what people would do for complex systems like VLSI design. And topics includes, in that particular case, embedded software design, what are the tricks on making good embedded software, interrupt and hardware interfacing, so more so the part that we just discussed before, the traditional approach, model-based design, representations for continuous and discrete dynamic systems, reasoning about concurrency and timing, real-time operating system, as well as system analysis and verification. What we will do in this class, we will not pick one over the other. We'll try to combine the best of both worlds. And we will learn embedded systems through a very much hands-on approach. I do believe that hacking and hands-on experience is the best way for you to learn how embedded systems work and how to become proficient with embedded systems. So we will really orient our lectures and labs toward getting hands-on experience in building a small system. And we will, of course, augment that with design methodologies borrowed from the cyber-physical system approach. As such, this class will be split in two main parts. We will have a first part of the semester that will essentially focus on lectures, where I will cover various topics related to microcontrollers and embedded systems. Lab sessions, where we will practice those new set of skills I just discussed about in class, as well as a homework that will be fairly time-consuming, but that consists in giving you the basic knowledge about how to make a printed circuit board and making, an embedded systems for real. The second part of the semester will be focused essentially on mini projects, where you will be able to implement the project of your dream using the skills we have acquired in the first part of the semester. So the course objectives for this class are the following. I will bother you with this slide during every single lecture, so we will see where we stand in our curriculum. We will get familiar with the ARM-M processor architecture. Why picking the ARM-M processor? I will talk in more details about that, but simply because this is one of the most commonly used microcontroller core in the industry at large. We will try to understand the architecture of a microcontroller, and things are very different than a microprocessor, and we need to cover those differences. We will acquire the fundamentals of hardware-software interface. How do I write a piece of software that does control my hardware? And we will also acquire the fundamentals of sensing and controlling the physical world. By doing so, we will basically try to learn how to implement, how not only to acquire sensor data, but what to do with them, and implement some feedback loops that will be able to control the complete system. We will learn modeling techniques for embedded system design, such as finite state modeling, continuous dynamics. These are very invaluable tools that you will have to use in your professional life to understand what your system, how your system should behave, so that you can show in the end that the system behaves as planned. And we will understand the usage of several peripherals through labs. So this is very much linked to the fundamentals of hardware, software interface, and microcontroller architecture. But here, we will really dig into the details. We will look at registers, how does that work, read through the data sheets, and implement some real application using that. And finally, I really want us to design from day one a complete embedded system, from the specs to its actual realization and obtaining a system. In order to do that, we will have to realize a PCB. We will have to model the behavior of our system and implement this system, a system that behaves as the specs. The system is fairly simple but pretty exciting. It consists of a complete DC motor control system. This is our the main goal of the first part of this semester. We will build an autonomous embedded system that consists of an ARM M0 processor that is embedded on your development board that is available in the stockroom. We will interface this board with a DC motor thanks to a custom PCB that you will design and fabricate. This PCB being here to implement the analog interface between the power interface between your DC motor and your control logic, as well as controlling the fine-grained details. And we will be able to implement on our system a complete PID controller that will help control the speed of this motor no matter the torque you ask on the DC motor. What will we do? Before we reach out to this point, we are going to build on several labs that will help us get knowledge of the different peripherals. For your labs, you will work in pairs, and you must partner with someone in your lab session. You cannot partner with someone that is not in your lab session because it gets very hard for the TAs to manage the lab time. I would definitely recommend to try and form cross-discipline pairs, student from CS with student from ECE. That way you can really merge all your knowledge and get the most out of it. Please make sure to have a CADE account for people who just started their instruction at the University of Utah. You should get that in order to access the IT system. TA will be present in every single labs, and we will cover various topics where we will, various topics of increasing complexity. We will first start with the ARM toolchain and building a very simple Hello World, and then we'll start building already on all the basic modules, in-chart management, control of timing, so timers, PWM generation, analog interface, DACs, ADCs, communication peripherals, UART and I2C, just to mention a few. And then we'll continue with our system modeling and the complete system realization. As I said, in addition to the labs, we will start immediately with a homework that will consist of several assignments. This homework will consist of you designing and building a printed circuit board. This printed circuit board will be used during the lab sessions. So the trouble that we will face is that we need to be pretty efficient and we need to get that done early in the semester in order for the PCB to be fabbed and assembled before we need that in the class. This PCB will contain an analog interface for the DC motor, as well as an I2C temperature sensor. It will be part of a real embedded system. It is a fundamental embedded system that you will build during the first part of the semester, even before you start building on top with your projects. On a side note, you will have to pay for board fabrication and components. Components are roughly $10, and board fabrication will cost you less than $10 a piece as well. In addition to that, we will do mini projects. Once we will be advanced enough with our lab schedule, you will be able to really build your own embedded system from scratch. As I told you, I'm a strong believer of the learning by doing, and I want you guys to pick a project of your dream and start assembling that. So you can expand on our motor control system, or you can go with something very different that will fit whatever interest you might have. You have to work in teams. Again, we're pretty flexible in terms of size of the team, between 1 and 4. Of course, the requirements will be very different for a team of 4 compared to a single person doing a project. You'll have to meet with your TAs and myself to discuss your ideas before you embark into the project itself. The topics should be related to the class, and most of our emphasized topics that goes with, drones, robots, all sort of controller you might have, but it can also be related to your research if you're a graduate student. I strongly encourage graduate students to actually pick a topic that is related to their research so they can make a good use of the project time for their own research activities. Same goes for senior projects. You are definitely encouraged to build something useful for your senior project during this class. Definitely the scope of project must grow with the size of team, and the evaluation will be based on that. Finally, one last thing to do is a literature review. This will be for graduate students only. This class being both an undergrad and a graduate student class, specific requirements must be put additionally to the graduate students. I will ask you to pick a topic related to embedded system and pick a topic of your choice. It could be wireless communication, it could be air quality sensor network, IoT cloud solutions, whatever that fits your interest, being it more EE or more CS. You will have to review at least 4 different product data sheets related to this specific topic, or 4 research papers in link with your selected topic. So for example, if you are picking LoRa communication, you might be able to review a couple of available products, LoRa transceivers, review the different performance and specs and power budget and so on and so forth, as well as mix and match a few research papers that will talk about application of this technology. You will have to write a summary of your review in the form of a scientific paper background section. You'll have to use an IEEE 2-column font 9 format, but be very careful. I'm not asking you to have separate reviews of 4 papers. I'm looking for a very cohesive literature review, considering a topic, illustrating its limitation and problems, and identifying a couple of solutions and explaining them from these different data sheets and papers that you have reviewed. We will also do an exam. You will be pleased to know that we will only have a unique exam that will cover the most important notions we have seen in class as well as in labs. It will also emphasize on problem-solving fundamentals. We will run during the semester a couple of Q&A sessions as well as exercise sessions that you will be using to practice in preparation for the exam. The tentative date for the exam is actually on Canvas. Please have a look and let me know if there are really strong concerns already early in the semester. Our grading policy goes as follows. We are putting a lot of emphasis on labs, as well as strong emphasis on labs, and then we kind of divided the effort between the exam that is pretty time consuming. I encourage you to start early, as well as homeworks. Specific grade assignment is made for graduate students because of the literature review. Lab assignments, we do have 5 different lab sessions running during the week with different TAs. Everything will be posting on Canvas, and please please find a partner in your group before the first lab, otherwise a partner will be assigned during this first lab. The labs will begin the second week of class, so the first week of class does not have any labs. The second week we will start with some help sessions for your homework, and we'll continue after that, starting our regular lab schedule. As a side note, the lab schedule has been adapted for the Monday group in order to accommodate the public holidays we will have during this spring semester. Hardware. You guys will have to buy a little bit of hardware for this class, and all the hardware will be made available through the ECE stockroom at the University of Utah. Here are the most important part. The most important things are to buy the STM32 Discovery board that contains our microcontroller, and that will be the main element for your labs as well as a project. You will also have to buy your custom PCB that you will build through the homework. Custom PCB as well as the part, and we'll use that for the homework, the labs, as well as the mini project in most of the cases. You are also encouraged to buy a USB UART cable that will be used for our UART lab as well as for the mini project later down the road. We encourage you to also buy a soldering demo board. This soldering demo board is very cheap, and you will be able to use that one to practice your soldering skills before you actually solder your PCB for your mini project. Finally, as an optional component, because it's relatively expensive, we invite you to acquire a logic analyzer. Analog to Discovery from Digilent are the product we currently recommend. The Zilla logic analyzers as well as pretty good. We are currently investigating ways for the stockroom to acquire logic analyzer that you will be able to check out during the class. We invite you though to acquire one. They have a pretty competitive discounts for academic use. The STM32 Discovery board will be our main toy, and this board is very cheap, around $10, and does contain a microcontroller, which is an ARM Cortex-M0 based microcontroller, along with a complete programming and debugging interface, the ST-Link V2, which will be extremely useful to load firmware as well as enter in debugger mode on our processor. It also offers a full pin breakout, which will be very useful to connect peripherals as well as to make your project a success. We also have a couple of additional buttons, LEDs, and a capacitive sensor that we will use across our labs to gain more experience with the system. The STM F0 Discovery Kit is actually pretty interesting. It does indeed contain an ARM 32-bit Cortex-M0 processor that can be operated up to 48 MHz and contain both flash and RAM memory. Peripherals are plenty, ranging from GPIOs that are 5-volt tolerant, analog interfaces, communication interfaces of various kinds. So this board is really useful not only for our labs, but you will be able to get most of it in your project later down the road, and you probably won't be limited by its functionalities. The kit's availability, so the kit will be made available through the ECE stockroom, and every single student must have this STM F0 Discovery Kit and a USB UART cable. Again, we recommend buying the logic analyzers. We are not carrying them in the ECE stockroom. You will have to buy them directly from the vendor. Things to remember as you will buy your kits and you will get excited in starting to play with them. Be careful not to short the board. You don't want to destroy your board even before we started using it. Using anti-static mats and connector in lab when handling the board will be fundamental in order to prevent ESD discharge on the input pins. Please ask your TA in the labs if you don't understand this concept. Make sure to ground yourself before touching the board, undug board very gently by the edges, and avoid any tasks that produce static before handling the board. So for example, it's never a great idea to use those boards while walking on the carpet, for instance. A couple more administrative items. We are applying a very strict lab report as well as homework assignment deadline policy. Your labs should be checked off during your lab session. And lab reports will be due on Canvas by the time of your next lab session. Please make sure to put your lab numbers, your lab section number on all your lab reports. And lab reports will be considered, as well as homework, will be considered late based on the timestamp on Canvas. So if you're not submitting them by the timestamp, we will consider them late and apply a late assignment policy. The late assignment policy goes as follows. First of all, you're at risk of not being graded on this assignment. We will of course do our best to grade it, but sometimes if things get out of hand totally and you guys decide to submit your reports the day before grades are due at the end of the semester, we will not be able to grade them. If we grade your homeworks and lab reports, we will consider a max grade of 75% for any assignment given late within a 1 week time period between the due date and your timestamp. If it goes beyond that 1 week period, your max grade will be 50%. All reports and exams will be assumed to be correctly graded 1 week after they are returned and grades are released. If this 1 week has lapsed, you will not be able to make any changes and no complaints will be considered. Before that, please reach out to your TA and graders if you believe a mistake has been made with your grading. The TA will look at your case and we will discuss what is the best way to resolve the situation. Similar policy applies to the homework, as I said, but with a much higher risk of not being graded because we are playing on such a stringent deadline in order to get our boards fabricated for the lab that we have to respect the deadlines. If you have any questions again about your grade, please contact your grader regarding the assignments to address the issue. Cheating policy. Cheating policy is cheating is not tolerated in this class. It is also not tolerated in the EC department. I have simply summarized on this slide what is a general policy, but I invite you to consider the exact cheating policy in place on our Canvas webpage.